incomplete. There's a problem that says implement Kruskal. I'm not sure it's extra credit or regular credit. Which one is it? Oh, that's a mistake. You should have made it regular credit. When is the homework due? Okay, I'm going to change it to regular credit. Okay, see if you can finish it by tonight. I'm not kidding. Let's implement Kruskal algorithm. Okay. So here's the thing. What did we have there? You don't have to finish by tonight. You know, I'm lenient about these deadlines, but I want you guys to implement Kruskal algorithm. There's several things that you have to figure out in there. So we said in Kruskal, there's some stuff that's connected already. Right? Right? And we have the MST theorem that says what? Anyway, you define a cut in here that doesn't crosses the existing edges. So these edges are the ones in A, right? Already. I already decided somehow that these particular edges are part of my MST. There's additional edges, of course, because otherwise I wouldn't be able to create a spanning tree. So I drew the cut. This is my cut. Right? And I say, what's the theorem saying? The next edge that you need is the minimum across the cut. Right? Fine. The problem in Kruskal is we have to define the cut. Remember, I made this list last time. We need to define the cut. And we need then to engineer the implementation. That is, what kind of data structure I'm using, how do I actually find the edge that I need, you know. It's, conceptually, we say it's the minimum across the cut. That's well defined. But then what's the fast way to find that edge? Or you know, like once we have conceptually what we want to do, putting it in implementation, which is what you're going to have to do, it's gonna require some effort. So somebody, him, pointed out at a way to defining this cut. Implicitly, you didn't say it that way. You said, okay, how about I do that? Turns out to be exactly Kruskal algorithm. Okay? So the minimum spanning tree theorem said, anyway you define the cut, you just find that edge over the cut, and then you're good. But in Kruskal in particular, there's a way to define the cut. It's not explicit. So we're gonna do this now. I mean, I still want you to figure out exactly how it goes, but I want to give a strong hint here. We're not gonna actually define the cut explicitly. A cut will be, say, how do I define a cut? Specifying exactly what nodes are on the left side and what nodes are on the right side, right? A complete definition of the cut will have to imply this. We're actually gonna implicitly define the cut. So we're not gonna specify what nodes are on the left and what nodes are on the right. But what we're gonna specify is the minimum edge across cut. So instead of defining the cut, okay, I'm not going to say exactly this is the cut. What I'm going to say is I'm going to skip the cut part and say which is the edge that once you define the cut, you're going to have. So suppose I put my hands on that edge and I say, I want to have this edge here. This is the new edge. For this to be working as a correct new edge, if this is the edge I want, I need to define the cut how? These two have to be on different sides of the cut. Right? But the cut still has to respect the rest of the edges and components, right? So this would be a valid cut. right? So what makes this valid new edge? What properties do I need? I need the U and V to be on different sides of the cut. What else do I need? I need the cut to respect the existing MST edges, the ones that are already there. What else do I need for this new edge to be selected across the cut? New edge has to be minimum across. This is the properties that the theorem, if I have these properties, it's going to say, okay, that edge is the one you need. So what he came to say after last lectures is, I know which new edge I want. Right? He was saying, I don't need a cut. I need that new edge. And I was arguing that new edge actually corresponds to a cut. First of all, is this cut unique? Can I define a different cut that would put up the same edge? Well, if I define a different cut, this cut is valid. It does set U and V on opposite sides. But again, I need this new edge to be minimum across the cut. So how can I, what's the idea? What's the new edge that I need? Can you pick, so what I said here is, can you put your hands on that new edge without actually defining a cut, but in a way that you make sure there is a cut that has these three properties? So I would like to skip the cut for implementation purposes. Just directly find the new edge and say, okay, I don't need a cut, but I know theoretically there is one cut that's good. So the theorem will say, okay, the edge that you just picked is good because I can define the cut, blah, 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 blah. But in an implementation, I don't want to define the cut. I just want to put my hands on the new edge. What should be that new edge? So I don't have a cut. I have no cut at all. And how can I say immediately that new edge, this particular new edge, by what criteria this new edge, it's certainly an edge that has these properties. There is a cut, it's valid, it's minimum across the cut, all of that. Minimum edge that has what property? That does not form a cycle. So that is actually Kruskal algorithm. The new edge is minimum edge that does not form cycle. How can I rewrite does not form cycle in a different way? Same thing, but I want to say that exact thing without saying does not form a cycle. Connects two disconnected parts. Any edge that connects two things that are not already connected, it's an edge that doesn't form the cycle. So some edges here, this is the new edge, some edges here are illegal, like this edge, right? This, even though that may be a minimum edge, it's not something I can use because it's already connecting something that's connected, right? So that is what we want. So this is the actual Kruskal mechanism. Pick the minimum edge that is not connecting two things that are already connected. How can I argue theoretically that this new edge satisfies the theorem, the MST theorem? So how can I, suppose this is the edge now that has this property, minimum edge that connects two different components. How would you define the cut?
The best way would be that whichever two nodes I am connecting, can I take the one of the node and can I create a edge around its tree, its subtree.
Okay, he's saying isolate this tree and make the cut, I think, this way. Right? That's a valid cut. It respects the existing edges. Right? Because I'm isolating that tree. Is this edge going to be across the cut? Is it going to be the minimum across the cut? How do you know? Why is not this one the minimum across the cut? Because that's the global minimum, and that would include these other edges. Any edge across the cut is included in when I take this minimum. So that's the global minimum. Is this the only way I can define the cut? In fact, any cut that separates those two nodes and it's not respecting the existing edges. So once I separated those two, I can go anywhere I want with this cut as long as I don't cross existing edges. Any one of these cuts will be a valid cut, will have this edge across the cut, the condition being those two nodes are on different sides. And this cut will be the minimum across the cut because it's the minimum across all edges that would connect two things. So this is for theoretical purposes. This analysis or this argument shows that that criteria for picking an edge is going to satisfy the MST theorem, therefore it's guaranteed to be a greedy good choice. But I don't need to define the cut explicitly, right? So that solves this problem in Kruskal. We don't actually define the cut. We just pick our edge, and we know mathematically there is a proof that that edge is good. There is a cut, blah, 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 blah. But we don't need in the algorithm the actual cut. We just needed to prove that the greedy choice is correct because it satisfied the MST theorem. So it's good. Now, how about this? Now that I have my Kruskal greedy choice, I don't need a cut. How this algorithm proceeds? How do I start by what? What's the first edge? Minimum global edge. So the first edge, so Kruskal. First edge is the minimum global. Then what? What's the next edge? The minimum that doesn't form a cycle. So I want to keep doing that, but how should I implement this? I want to keep picking the minimum that doesn't form a cycle. So, how?
Use a T.
What was the idea last time? First thing first. Do what? Sort the edges. Okay, let's keep this. Sort edges. How long that takes? E log E in general sort. Now, if those edges have a range or a discrete structure or some property, maybe I can sort it faster. But if they really arbitrary real numbers, I have E log E. So, then loop. Right? I'm going to say eliminate. So loop by edges. So I go through all these edges, right? And I say if edge is valid, what valid means? No cycles. Then add it to A. Add to A. A is the set of edges. So this is a linear loop, right? Because it goes through every edge of the iterations. But then once I add an edge to A, what do I need to do? I need to do something. Right? Once I decided, okay, that's my new edge. So these were a component here, this thing. Once I decided these two components get connected, I have to do what? say somehow that this now it's a whole component, right? So I have to union the two components that are joined by the edge. And how do I check validity? How do I check if the edge has no cycles? How do I say, I mean, conceptually we know what that means. Like, if I already joined those two things, now this edge here, from say here to here, that's going to be an invalid edge because it formed a cycle. But technically, in a program, how do I check these no cycles? I don't like that. Too expensive. I've already had these components organized. Think of them as sets. They won't be a set in your implementation, but suppose the components are sets. I know each vertex to which component it belongs. How can I immediately tell if they form a cycle? If the two U and V belong to same component, same set, right? So this condition here, I'm going to rewrite more programmatically as, okay, in a program, if component of U is the same as, so the edges, if edge UV, how do I check? If component of U is the same as component of V, actually I want different, right? Valid means the two components are different components, and union means what? When I say union, what do I actually do? I create a new component that is the component, they say join, component of U with component of V. So now we solve the actual pseudocode for Kruskal. This is much closer to a pseudocode. You guys know how to do sort. Then you traverse the edges in that order. Then we say it's valid, means I need to check if the two nodes are in different components. And then if they're not, I select the edge and I join the two components. So later on, those two counts as the same component. What is the tricky part here? What's the data structure for the components? And can I say this whole thing could be O of E? Is the inside part of the loop constant? Is this constant? Checking the two components? Is it going to be constant? Yes. At the edge, constant. How about the joining part? That depends very much on what data structure you're using. Joining two things might take more than constant time, right? So that is the engineering detail that you guys are going to have to figure out. How do I represent these components, these sets or trees or whatever I have, in a way that the joining operation is fast? Okay. And then you don't want to sacrifice this. Maybe you do this very fast, but then checking if two components are the same, that will be very slow. That's not good either. Ideally, we want these to be, because I do a check and a joint, right? So it comes down to which one is the most difficult, right? Maybe joints don't happen all the time, right? This will happen all the time, but this will only happen when I select a new edge here. So I want some sort of data structure that allows to do both operations very fast. We don't do this explicitly in class. There was a chapter in the book, I'm not sure it's still there, union sets. So that's the most efficient way to do it. Now, in your implementation for Kruskal, I won't be picky about this, but if you want to do it perfectly, you need to figure out how to represent sets in a way that the union works fast. and the membership check. It's also very fast. Okay. So that's what I have to say about Kruskal. So back to where we are. Yes.
So the membership check should happen ideally within constant time. The membership check and the.
But I would imagine this for that purpose. This could simply be an array. Comp the u will return an ID, which is the ID of the component for u. So I need an array of v slots for each vertex, and component the u will return 1, 2, 3, whichever is the ID of that component. And if they return the same ID, means they're in the same component. But then when I do the joining, if I maintain an array, I would have to say, okay, everybody in that component, everybody who has the same component as v, changes the ID to that ID. So I take this ID component of u, ID number 12, and I say, okay, everybody in that component, not just v, everybody in this component gets that ID 12. That will traverse the whole array part of v, but I need to know which other vertices have that ID, right? I take this ID, suppose this is ID 12 and this is ID 17. I have to go through all the vertices and say, if your ID is 17, I update that ID to 12 to make everybody has the ID 12, right? But that includes a traversal of the array, that's V. I have to go through all the vertices, check their ID, right? Ideally, I'll have to go only over the vertices that have 17. So I need to, maybe if I keep two arrays, one that from the components gives the ID, the other one that from the ID, it's a list of vertices, right? So if I have a list vertices corresponding to ID 17, will be a set V1, V2 up to Vk, then I only have to go to this list, not through all the vertices, and change these IDs from 17 to 12. And then what do I do with this list? I destroy this list, but I append this list to the list of 12. So that's keeping two structures, one from vertices to the component ID, but the reverse one from the component ID to the vertices. And that will have to do a global analysis. If I keep those lists, how many times I go through each vertex. Because one pass may be a lot if this is a big component, but then you guys have to figure this out. You probably want to work on the smaller component. If I join a small component to the big component, it may make more sense to go over the small one. So implementation details. I don't have to do that. I don't write programs in the algorithms class. Only the students do. Right. So easy for me. Okay, minimum spanning trees. That's done. Now we are at shortest paths. Before I connect my projector here, I want to get back to the relaxation property. So in the shortest path problems, we always have ESP from S to V. Sometimes S is not written because it's a global S. We care from shortest paths from a given starting point, but sometimes we don't have a starting point, so we have to specify that. That is the shortest path from S to V found so far. It doesn't mean it's the minimum shortest path. It means out of my exploration through the edges so far, that's what I have. So if you want to think about this way, so far I have in V ESP equal to, what did we say, 20. And I have a different U with an ESP equal 10. And when I see an edge from here to here of some weight, say 7, how is the relaxation going? It says if ESP from S to U, this, plus the edge of UV, so this is W UV. If this is smaller than ESP from S to V, then I do update or relax. I'm making the ESP of S to V equal to the ESP SU plus the HV. That's saying it doesn't mean I found the shortest path. It means I found the better one that I had before. Because I had the one that's 20, but this is like 17. Now, like in dynamic programming, ESP is like that C, keeps track of the value. But that's not enough, right? If I say shortest paths, I may mean not just the value of the shortest path. I may actually need the path. So if I want to do that, I have to keep track of something. Like in dynamic programming, remember we had to do tracing, the solution? Because updating the objective, while that's correct, it only prints the objective at the end. So we needed something to keep track. So what would I keep track? If I want to keep track of that, how do we call that? S, okay, to tracking. If I want to keep track of something, of my new SV, my new path to SV is going to be 17. That's updated here. And what should I keep track of? The last edge used. When I say you want to go from S to V, what is the last edge that you just used to have 17? What's the last edge? And then, of course, if I know this is the last edge, it means the previous node before V was U. So then I will have from here the last edge to get to U. And I keep tracking backwards all the way to S that way. Right? So just like in dynamic programming, if we want to keep track of the path, not just the answer, we need to keep track of the previous node or the previous edge, something like that, with this relaxation. So this is essential for all shortest paths algorithm, this mechanism. How do you update the path that you have with a better one? Then we said, okay, there is a fundamental theorem, just like with the MSTs. There was a fundamental theorem that was saying what? In order for anybody to find the shortest path, so if I want the shortest path from S to T, and this is the actual shortest path, actual shortest path, B1, B2, B3, B4 up to Bm or something. Shortest path is found if the edges of the path are relaxed in path order. So this is relaxation of edge UV. So there's a theorem that says if you want to find the shortest path, what you have to do is to relax these edges, but in the order of the path. In other words, if you relax this edge, you'll already have found the shortest path to V1. Maybe you don't know that you found it, because in the middle of the relaxation, you wouldn't know that's the shortest path. It's possible that later on, because you don't know that, it might be another path. But this, once you relax this edge, this ESP will never get shrinked again, because you already found the shortest path. Then after relaxing this edge, you need to relax that edge. And then you have found the shortest path to V2. And then relaxing this edge will find the shortest path to V3. Right? That's because this is an optimal solution structure here. That says if this is the shortest path, from S to T, passing through some node V. If this is the shortest path, then S to V must be shortest path, and V to T must be shortest path. Very simple exchange argument. If there will be a better path from here to here, I put that in, I get a better path for all, right? So shortest path implies shortest path from S to V and shortest path from V to T. So we need to relax these edges in order to get the shortest path. But of course we don't know the order, because we don't know which one is the path. So the first algorithm that we discussed was saying, okay, starting from a point S, that's my starting point given. How do I relax first all the first edges on each path? There's a bunch of shortest paths going everywhere. And I need to relax first just the initial edges. That will be all edges like the first edge of the path. There's some paths going that way, some paths going that way. So how do I relax these edges just starting from S? I don't know which ones are those edges, other than that they connect to S. There might be some edge that's in the graph, but is not included in the shortest paths anyway. Remember how that went? How?
Started with like relax everything.
I relax everything because relaxing everything is guaranteed to relax those 5 edges. That's a pretty gross, like root. Way of doing it, but relaxation, right? That's what we talked about. So what did we say? Relax all edges. That's guaranteed that I'm going to relax the initial ones. Then I need to do what? What do I need to do after this one is relaxed? Now I know the first edges are relaxed. I need to relax the second edges. But didn't I just relax the second edges the first time? I did. I relaxed all of them. But what's the problem? So what I need to do now, this is round 1, right? And then from here, I have other edges going to some other. This is all part of the shortest paths, right? Because the shortest paths will form a tree. Now I need to relax those edges. How do I make sure I relax those edges? This 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How do I relax those edges? I relax again, all of them. But why do I need to relax them? Didn't I relax them the first round?
Order.
I relaxed all edges the first time. Remember, because the first time I relaxed all of them. What's the problem with that? I couldn't guarantee that I relaxed the round 2 edges before round 1 edges. Right? Does it make sense what I'm saying? But can I do a BFS starting from S to make sure I keep that order? Say I start from here. I relax all edges adjacent to S first. Then all edges from there second. Then all edges from there third. Can I do that? So you see why I need to do those multiple rounds of relaxation. The only problem, I only need to relax all edges exactly once, if I could do it in the right order. If you want to think of waves, this here is wave 1. This edges needs to be relaxed first, before the wave 2. This here will be wave 2. The problem is, if I say relax all edges, is that I need to make sure I relax them in the right order. Meaning those 5 have to be relaxed before those 11. Now, Bell-Manford does it very gross approximation, saying, okay, I don't know which ones go before which ones, so I'm going to relax at all rounds, all edges. That's guaranteed, and those 5 are going to be relaxed that, because round 1 relaxes all of them, including those 5. Round 2 relaxes all of them, including those 11, so on and so forth. But can you be smart about it? Do a BFS, starting in S, and say, I'm only relaxing wave 1 BFS edges, which may be a little bit more, right? There may be another edge here in wave 1 of BFS, but I'm only relaxing few edges more, not all the edges. And then once I have BFS round 1, I advance BFS, I say, okay, round 2, wave 2 of BFS, relax wave 2 edges. Is that correct? So is it possible that here, so that's I think that's incorrect, because here's what happened. This in a shortest path, this would be a what wave? 3, right? Is it possible that in BFS this edge is wave 2, so it gets relaxed out of order? It's possible, because I may have an edge here that's not the shortest path edge, and this gets relaxed in wave 1. That doesn't bother me, it's an extra, but then this gets relaxed in wave 2 of the BFS, which is not necessarily before this, after this one. So it'd be nice to have an intelligent way. I think we all realize here that I need to relax every edge exactly once, if I'd be smart enough to do it in that order. But I'm not. So maybe you guys can find a way to do it. So let's look at this example here. And I start in that point, that's wave 0, right? And the numbers on the edges are the weights. So what happens if everybody is at ESP infinity initially, because ESP is the shortest path I think so far. So far I haven't seen a path, so it's infinitely far away. This is what I want, right? Those are the round 1 edges, right? But I can't just relax those edges because I don't know which ones there are. So what happens here, I relaxed all the edges, not just those, but those 4 are the ones that matter for me. See, the algorithm, when I run it, wouldn't know which 4 matter. But if I look globally, I'd say, you can tell I relax more edges because see this 7 here? This is because I relaxed this edge. But this is not necessary. This is not part of the shortest path 3, so this is just an extra. Right? Did I relax this edge too? I did. But why this number is still infinity? So the relaxation procedure went to all edges, including this edge over here, these 2, right? But why did not change anything? Because infinity plus 2 is still infinity, right? In here, what happened? This 1 got updated after the 2. So when I relaxed this edge, I still had infinity plus 2 equal infinity, so it didn't change anything. The only edges I need are the ones in red. Now, so this 7 is irrelevant here. What I'm going to count on is that these now are the shortest paths, these numbers in red. So when I do the relaxation the second time, this being the shortest path to here, when I relax this 4, which is an edge that I need. This is one of the second round edges that is part of the shortest path 3. I get 1 plus 4 equal 5. Now the algorithm doesn't know that this 5 is the best it's going to get. But I know, globally speaking, as an analysis, that this 5 will not get relaxed any down. There's no other path that's going to relax this 5 down. So now I already obtained the shortest paths to all numbers in red. See this 8? This 8 has been relaxed from this 1 plus the 7, it's 8. So the ESP worked in here, right? I have the ESP equal 8. Why is not in red? This is not part of the shortest path. The shortest path is 1 plus 3 plus this 3, right? But I need to relax this edge to get that property, right? If I relax this edge, what's going to happen? 3 plus 3, 6, better than 8 is going to update this. I already relaxed this edge twice, correct? The first round and the second round because all edges were included. But it didn't work because it was not before this other, the 2 edges here, 1, 2. The only relaxation that matters on this edge is after those 2 were performed in order. Because the relaxation must happen in the order of the path to get me the shortest path value. So when I relax it the first time, I get now shortest paths everywhere. Because all shortest paths, so you can see the tree. Starting from here this way, starting from here that way, this. Yes?
So, in this case, there is a possibility that even if something is 3 steps away, it can be relaxed and reach to the minimum even in 2 steps.
Because the order might happen that way. If I'm lucky and the first relaxation happened to be in this order, when I say relax all edges, maybe I'm lucky and I do it in that order, then I found the shortest path the first round. Right? But I can't promise that. How many people with me? Okay, questions then?
I didn't understand the first iteration, why we did not consider the 7.
The 7 here in the plot?
In the initial
the
first
first
round.
Because
Yeah.
there is a part.
Which? This 7?
Yes.
No, we did relax it. You can tell the plus infinity has been changed to 7.
No, but it was not highlighted in red, so I was.
I'm only highlighting in red the ones that I know are part of the shortest path. The algorithm internally wouldn't know they're part of the shortest path until the very end. So the algorithm keeps updating. It doesn't know I found the shortest path or not. The red is just me putting the red edges. But the algorithm doesn't know these are the shortest path. As far as the algorithm knows, there might be a better way to get there. But the thing is, I know this is the global minimum, and it's never going to change. So that edge will remain as part of the shortest path edge. So that's a good point. The red thing is not part of the algorithm. It's me annotating this, saying this is never going to change. This 7 is going to change. That's why it's not in red, because there's a better path to it. Okay? Good with this? Okay. So how many times do I need to do this? Well, the maximum path theoretically is V, right? So I have to do it V times, and then V times E, because each relaxation includes all edges, it's V times E time, right? Okay. There is one graph in particular for which I know the order of the edges that needs to be relaxed. So remember what I said, I only need to relax each edge once if I know the order. In general graph, I don't know the order, so if I do Bellman-Ford, I'll relax them many times. There is a particular graph for which I can tell you each order of the shortest path. The paths that can be sorted on a line, aka tags. We have topological sort, we can sort on a line. In here, what's the right order of the edges that every path, or every shortest path, but in fact any path of any kind, will be in that order? By doing left to right, meaning this edge these edges happen before the next edge, so on and so forth, I think I can easily show that every path gonna be relaxed in the order of the path, which means I only need to relax the edges once in that order. I got all the shortest paths. Easy, right? Remember that every time somebody says a DAG to you, before even he says the next word, that person, in your mind, boom, topological sort, right? As soon as somebody mentions this word to you, a cyclic graph, you immediately have to think of it on a line. And recall these kind of things. Shortest paths, dynamic programming, lengths, whatever. Everything is much easier if the graph is sorted on one line. Okay. So here's the relaxation of the edges, right? I do the leftmost ones first. So this will happen before this, but between those three, I can choose any order, right? Between those three edges, there is no order between them. I probably safer to just start from the leftmost side. I relax all edges from this vertex, and then all edges from this vertex, and then all edges. So make sure that every path I found is in the correct order of the path. Okay, so that being said, now let's do something smarter here. Right? So Bellman-Ford end up being V times E because it relaxes all edges. That's E times V times E. How can we do this better? I still have a current, I want to think of Prim algorithm. Prim algorithm for MSTs maintains a what? Minimum spanning tree. In here we don't have a minimum spanning tree. We have a shortest path tree. And we already said last time that those two things are not the same. A minimum spanning tree does not produce the shortest paths between the vertices, and the shortest path tree is not a minimum spanning tree necessarily. But let's suppose somehow, magically, I don't think we need a projector. Somehow, I have the shortest path partially. So I don't know how, but this is all done. I have these ESPs, right? Let's say the ESP here. So the ESP, it's actually the shortest path. And I know that. I'm not sure how am I going to know it, but suppose I know it, right? Now, what's going to happen? This is my current wave, right? I've got to here somehow, say. So this is the shortest path tree. This is starting in S. So I'm having a starting point here. And I wonder, how can I advance this tree? Just like Prim does, right? Prim connects a bunch of things and then says, okay, how do you connect the next one? What does it do? Minimum edge that attaches to the tree. Fine. So I want to do the same, but in the shortest path and say, this is the shortest span that you already found and they're done. Like for some reason, I know this is not just like in the Bellman-Ford. The Bellman-Ford, I have these ESPs, but I never know they're going to shrink or not until the algorithm finishes. I don't know those red edges until the end. In here, suppose I know the shortest paths to these nodes, it's done. So I have a bunch of ESP values, right? ESP, this is a 10. This is a ESP, that's 15, I don't know. ESP, that's 12, so on and so forth. Maybe this has a 100 in it. This is a 25. This is the 2 here. This is a 80 and 50. So suppose that's what I have. And I'm like, okay, how do I move on? Where should I continue the shorter spans in here. So all these guys have next edges that I could consider, right? Of course, I don't want to go back, because if I already know those are the shortest paths, I won't go back here. So say they connect to some nodes. How should I proceed? If I know the ESP of this is, say, 100, and I see an edge here that is 5, what would be my estimate for here? 105. But I may have another edge that's coming from here, right? That would be, say, 10. In each case, my thing would be 90. Right? So I can't. How can I this is my current one, so I drew this circle that's already done, and then I want to expand this. I want to go to the next round, right? Next wave or something. How can I figure this out? Can I just say pick this edge or that edge? What if there is, from this 25, there is a bunch of edges that they all like 2, 2, and 2? How the ESP would be here? That would be a 31. Right, so I don't need to make sure I get the shortest path. I'm only doing sequence of relaxations, even if I don't pay attention to this part of the graph. Say I look this way. I do 100 plus 5, 105. Later on, I have to find this, right? Later on, I have to say, okay, if you find, eventually I'm going to find this node, which is 27. Then later on, I'm going to find this edge, and I'm going to give me 29. And later on, I found this edge, I'm going to get the 32 in here. Okay. But how should I proceed? That's the critical part in Dijkstra. What needs to happen in these relaxations? There is a general problem for the relaxations that makes them don't work. Back to Bellman-Ford for a moment. Why is it that if I relax those edges, I cannot use this relaxation for this edge? It's essentially a waste of time. When I do it the first round, even though this edge gets relaxed, why is it that I can count on that relaxation the first round? I have to do it again the second round. What's the reason? I can't promise that the first edge has been relaxed already. So in reality, what does that mean? If this edge was not relaxed when I relax this one here, the number here is not the shortest path. It's some ESP infinity or something. So I can update this. I can say, okay, this was a 20, I don't know, an 8, and I see this one a 5. I'm going to make this one 13. The problem is this is useless because the 8 is not the shortest path, which means when I relax this edge later on, I'm going to get here a 5. Then I need to relax this edge again. Relaxation is only good if this is already the shortest path. Any relaxation that starts from somewhere where it's not the shortest path, maybe this value is going to change later, it's going to go down. That relaxation was a waste of time. Because it doesn't serve me if this is an 8, 8 plus 5, 13. This is not interesting. Everything I do at 13 from here next, that's not going to help, right? So, but when this is the true shortest path, 5, when I relax this edge, I get a 10, and that's the correct shortest path. So relaxations, while you can do a lot of them, they don't hurt you. They're only good when the node that starts the edge is already at the shortest path. Maybe there is a mechanism that says, so what's going to happen? Suppose I relax this edge at 8. 8 plus 5, 13. Is there a mechanism to say, if you relax this edge and this goes down by 3, everything from here goes down by 3. Right? In other words,
Yeah.
find some data structure that allows me to do this. To say, okay, there is a bunch of things that got relaxed. This 13 dependent on the 8. If 8 goes down, everything in that tree from 8 have to go down. The problem is, if something was not depending on this, depending on something else, I can't really go put it down if this goes down. There are some fancy data structures that allow you to do that with a lot of tracking. But we'll not skip them for now. For now, we'll skip them. What it's important for you to see is why some relaxations are not useful. Because they are done before the shortest path is found. I need to do the relaxation from U to V after the shortest path in U has been found. So that's a real danger to say, I relax this edge, I'm good. Yeah, but you relax it too early. You didn't have the shortest path. If the ESP changes here, you need to relax that edge again. Maybe you could say, fine, every time I change the ESP, I say relax all edges from that point. Because all the relaxations I've done from this point, if I change the ESP, I need to redo them anyway. That may be too much work, right? If I do these relaxations and then every time I change the ESP value here, I have to redo the edges from that node. How many edges? Because an edge might be relaxed many times that way. The value here might change 3-4 times. That means all the edges from this node I have to relax 3-4 times. So now back to Dijkstra. Even if I have this as a done deal, the danger is when I do this relaxation to know for sure that this is the shortest path. Right? I don't want to do relaxations unless I'm sure this is the actual shortest path. I'm okay to do extra relaxation, like if I go through an edge that is, okay, this is not the shortest path edge, like in this case. This 5, 1, it gives me 1 or 5, but later on there's a better path. I'm okay with that because I have to check this edge anyway at least once. So as long as I checked it after the shortest path was found, I'm good. I don't want to check edges for which I'm not sure I found the shortest path because those are almost sure a waste of time. When this value changes later on, I have to redo all these relaxations. So I'm going to repeat myself just to emphasize the point. What's the problem in doing relaxations is doing the ones that start from a U that I don't have the shortest path. So Bellman 4 does a lot of extra work because it does a lot of relaxations for edge UV. U doesn't have the shortest path. All those relaxations are naive, are useless. So in Dijkstra, we would like to do this. Do relaxations, even if some are not interesting, but only when I know for sure that I have the shortest path. So if this is all done, I could do the relaxations from all edges starting from this node. So if I know for sure those are truly shortest paths, I could do these edges starting from them, right? All of them. Starting from, this will be like my frontier, like in BFS, I have a queue. This is the shortest path that I know I have found. But if you do crawling, this is the peripheria of my crawl, what websites I crawl. And in this queue, I know I found the shortest paths. Therefore, I can safely relax all these edges coming from these nodes, right? And those relaxations are not wasted because I know the U was the shortest path. But what's going to happen in here? Can I tell those are the shortest paths now? The new round, where I went with my. So I've got all kinds of ESPs. Some of them might be updated twice, right? So in this case, there were 2 edges. This was a 5 and this was a 10. The first, when I relax this edge, if I do this first, I do 1 or 5, but then when I relax this one, I get I did 90. I may relax this edge first. In each case, I get a 90. When I relax this edge, nothing happens. right? Fine. Either way, I end up with 90. In here, I may end up with 101, so on and so forth. I end up with values. Can I tell that those next round, can I say, okay, the next round now has the true shortest paths on it, so move on. Can I say that? Can I say that these outsider nodes now are shortest paths, the ESPs in those cells are truly the ESPs? Why not? Why can't I do that?
Can be other paths.
There could be some lengthy path, like I said here, right? With a bunch of nodes. That's actually the shortest path. And I didn't find yet this because I didn't go through all these edges. So my plan seems interesting. I have this tree that I'm growing like prim. As long as I know these are true shortest paths, I can, no problem, relax the edges coming from them, expand one level. The problem is the new periphery at the wave 4 in here, or 3. Can I tell that those are true shortest paths to keep going with this algorithm? No. So how does this Dijkstra thing work then? That would be really nice, right? To say, okay, this is now done. It's good shortest path. Keep going from there, right? The problem is this new round is not yet finalized. So anybody remember Dijkstra from college years? How then, right?
You extend only by one node.
So he's making a point here. Why do you need the whole level to be clear shortest paths? You only need to know, okay, this guy here is the shortest path. I'm not including all the levels. If you tell me, okay, I know for sure this is the shortest path, I could continue from here, right? In order to continue, I don't need the whole wave to be ESPs to be final shortest paths. All I need, one way, one new node to continue from there. And I only need one node at each iteration. If I have a one node, I could continue from there. So okay, I don't need all nodes to be shortest paths, all the new nodes, I mean, these ones. I only need one node to be the shortest path. Okay? Can I find then one node? Can I tell, okay, this node has clearly the shortest path?
From the periphery, you find all the connecting nodes and find the minimum, which is a minimum edge to the next advancing node. Or you consider that.
So assuming again that I have the shortest paths all done in here, I can do all edges from here. Although that seems to be not possible this way to start it, because if I can't promise the next wave all to be short paths, how did I have here all of them being shortest path? Algorithm has to go with a principle that maintains, right? If I can't promise the next wave, I can't say I have the previous wave. But suppose I have that. I relax all edges, I get some new ESPs at the next wave. Is there any node in this next wave that I can tell for sure that ESP is the shortest path?
If it just has one incoming edge.
But maybe not, that's true, but maybe all of them have more than one incoming edge. I mean, that's in a graph, everybody can have many incoming edges. So, what?
With the shortest way.
Minimum what?
Global minimum age.
Age?
Yeah.
No? Somebody was saying?
The shortest number is.
Does minimum ESP. So I think the proposal is this is the minimum ESP on the new nodes. Right? Or maybe minimum ESP in general. Can I say the minimum ESP gotta be a shortest path for sure? That's what I want. If I can get one node that I can expand from, I can just keep going from that node. But can I say the minimum ESP is guaranteed to be the actual SP? You guys don't remember Dijkstra from college years. Yes, I can. That is the genius of Dijkstra algorithm. The minimum ESP must be the correct shortest path. That's only true for the minimum, not true for the other nodes. So if the minimum in here, what was the minimum before expansion? 12? Is 12 the minimum?
Yes.
Of course, it's the minimum that's not yet expanded. There's another minimum here that's a 5, but this 5 is done. Everything has been relaxed for 5. So when 5 was the minimum, I've done those edges, it's done, right? This is the minimum ESP, not relaxed yet. So how about this case here, where I have this 5, this 10, let's say this minimum ESP is 12, right? I get this edge, let's say that's 20. I just said the minimum speed is the shortest path. I hope you believe me. We'll have to prove that, but let's assume it's true. So this is my minimum speed, right? This plus 30 will give me what kind of value here? 42. Now, is this 42 a minimum speed? There is still this route that's better, right? 2, 2, 1, 1. This will give me what? 31. Right. So minimum SP, I say, is the shortest path. We'll prove that later. I'll have to expand from this guy. Because remember, I can only relax when I know for sure is the shortest path. All relaxations from when I'm not sure may be a waste of time. So I relax from here. I get the 42 here. Okay. And then this 42 is not the shortest path. How do I know that? Okay, in other words, what's the minimum after I've done the expansion from 12, I go to all kinds of things here. 50, 20, 40, right? I go to these values. So this would be, what, 62, 32, 52. What's the minimum now after I'm done with this 12? Let's assume I don't want to work on this side, so this will be 30, 50, 85, 80, 100. What's the minimum? I think this is 25, right? Left. So after finishing this minimum SP, even though this didn't get updated, right? I didn't have an age to update this. Out of a sudden, I'm going to claim, hey, that's my new minimum ESP. This got to be the true shortest path to here. Simply because it's the minimum right now. So I need to prove this property that the minimum ESP, it's actually a correct shortest path. But then this minimum ESP, what's going to do? It's going to update something to 45 and something to 27. Can I say this is the minimum ESP now, 27? I'm going to say this is the minimum, because it's the minimum global ESP, this is the one you need to expand from. 27 gotta be the correct shortest path. Now you can see how, before I consider this as minimum ESP, which is incorrect, right? I'll actually update the path through here, right? Before I get to this to say that's my minimum ESP, I'm going to have to run these updates first. This will be a 29. This will be a 30. This will be a, so it's cutting 42. It's going to be 31. And only now that I found the shortest path, if this is the minimum, I can expand from here. The principle again is you want to expand or relax, expand the tree by relaxation, only when you're sure that node that you're relaxing from, it's actually the shortest path. And how are we sure? We have this theorem that says minimum, it's guaranteed to be the true shortest path. So we can only expand from the minimum. So why is it that if this is a minimum, it's not possible to find a longer path to it? A longer path that's more edges, that's actually a shortest path. So Dijkstra, impossible. That is the, Dijkstra says, so far we found the minimum ESP. Minimum ESP, we claim in Dijkstra, it's actually a shortest path because it's the minimum. We don't claim that for any other node, but we do for minimum ESP. So suppose the tree only goes so far, the short spanning tree. Why is it guaranteed this shortest path? Is it possible that some path through here that I didn't see yet, right? There's a bunch of nodes on this path. Is it possible that this, I'm going to put some question marks. Is it possible that this somehow gives me a better shortest path? Is it possible that this minimum ESP is currently 100 and somehow this was here a 20 and this was a 2, 1, 3, 1, 2, 1. So if I add up all these edges, I'll get smaller than 100. Why is this not possible? This is the minimum ESP so far? No. Because this path leads to less than 100, something on this path, all of them on this path must be less than 100, right? So then the minimum ESP is either on this path or has been all expanded. But if it was all expanded, I would have gotten here. So the reason this path was not found is because this new edge here was not relaxed. But that means this node must be smaller than 100, right?
Bigger. It's bigger.
No. If I would have found a smaller path, this would have had to be smaller than 100. And its minimum ESP is here, it's not there. So the minimum ESP is guaranteed to be an actual shortest path, which makes it safe for relaxation. So now suppose this is truly the minimum ESP. So this is 100, but everybody else so far is more than 100. Everybody's more than 100. I relax from here. I'm going to repeat what I said there. I relax all edges from here. I may have some edges to here, right? Because this is maybe not done. So this might be currently, maybe this was 200, but I have a 10. So now this becomes 110. After I relax all edges from here, I get ESP values, right? ESP, 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 ESP. Again, this might point to some other things that I've already done. Maybe through this path, the ESP was bigger, but 100 plus 3. Now I got the 103 coming this side. Can I say again, out of all the ESPs I have, the minimum is guaranteed a shortest path? So what did I do? I take the minimum ESP and I say that's the shortest path for sure. Expand from it. Relax all edges from there. Why I do that? Because I want to do relaxations from nodes which I have for sure the shortest paths. I don't want to do relaxations when I'm not sure I have the shortest path already. Now, after I got all this ESP and some old ones, there is some other ESPs around here that I didn't have nothing to do with this node. Globally looking at the minimum ESP, can I say that's for sure the shortest path? This proof is required in the master course, not in the other course, but in the master course, you have to be able to prove this property, that the minimum ESP is guaranteed to be a shortest path. That's going to happen. If the minimum ESP happened to be this guy, this has to be a shortest path. The value there is the actual shortest path value. Because again, if there will be some other way to go there that will give me less, if magic there's a path that I haven't found yet, where would the minimum ESP be? Would be this node here.
Yes.
Because I'm assuming all edges are positive, right? So that if the value here will get better by adding those edges, then this current ESP here will have to be smaller than this ESP because edges are positive. So that there is a constraint in Dijkstra algorithm. All edges have to be positive. Was that a constraint in Bell-Manford? No. What was a constraint for the shortest path problems in general? No negative cycles, because then it doesn't make sense. You can just cycle the cycle and get a very small value. But negative edges make sense, just don't work for Dijkstra for this reason. This one is an exam question a few years ago. What's the reason that Dijkstra can't take negative edges? The reason is, in order for me to say the minimum shortest path is guaranteed an actual correct shortest path, means that everybody else bigger, if this is 100, I don't know, 100 plus 5, this is 105 now. If this here is 120, I want to say there is no way to have a path from here to here that results in less than 105. But to say that, I have to have positive edges, because if these edges are negative, then it's possible 120 plus a bunch of negative edges to give me less than 105. In order for me to say 105, the smallest, guarantees the shortest path, it means the edges have to be positive. So this is a quite abrupt limitation of Dijkstra. Dijkstra is an efficient algorithm, but many graphs can promise only positive edges. Some graphs do, things that have to do with natural quantities like bandwidth, quantity of water, transportation costs, all of it. There's no negative costs, all costs are positive. But remember that this proof is required. Why is it that the minimum is guaranteed to be a shortest path? Now the algorithm is not hard, right? Just pick that minimum and expand from there. And then look again for where's the minimum, relax from there every edge, look again where's the minimum, relax from there, right? So I need a fancy data structure for keeping track of this minimum, right? Once I put my hands on the minimum, relax all edges from there. Easy. So how many times I relax each edge? I pick the minimum ESP, relax all edges. Are those relaxations guaranteed to be good? Yes, because the minimum ESP was the shortest path. Am I going to have to relax these edges again? No. So edges get relaxed only once. The problem is keeping track of that minimum. Right? Once I do my relaxations, I have a set of ESPs, including the previous ones that didn't get updated. How do I keep track where the minimum is? Right? I need a fancy data structure that will do this efficiently, like a Fibonacci heap wave. Okay? Good. So that's Dijkstra. You still have to get the details of Dijkstra. I know, the pseudocode and that, but that's easy. If you, the tricky part in Dijkstra is this theoretical property. Minimum ESP, let's write here, theorem Dijkstra. Minimum ESP is actually the shortest path. This is what allows Dijkstra to keep going. Pick the minimum ESP. I know that's a true shortest path, so relaxation is good. It doesn't waste my time right now. Then again, I have ESPs. I pick the minimum. That's good. Keep going from there. Okay. We can talk more about this at office hours, because there will be some Dijkstra questions. The next thing that we want to do here is all source, or sometimes this is called pairs, shortest path. So far, the two things that we've seen was for a given source. Given S, how do you expand from there? Two algorithms, Bellman, Ford, and Dijkstra. Dijkstra is better, except it only works positive edges. What if I want to compute everybody? Right? Here's a naive version. For all S's as source, run Bellman Ford. I'm assuming a general graph from S, done. Bellman Ford to give me the shortest paths from S. I do it for every single S, so I get done. How long is this gonna take? Is V nodes, because I run it on all nodes, times Bellman Ford was? VE, right? So that's Z squared. Not that good, but at least if you implement this algorithm, you're not going to make any mistakes in the implementation, right? Because it's easy. Bellman Ford is very easy. This is just another loop on top of it, right? Okay, let's not do that. How about that property that I was saying, dynamic programming, remember? So from U to V, I want dynamic programming algorithm. So C of UV is the best path, shortest path between U and V, the actual length, the actual sum, right? Is the sum of the edges on the shortest path on the weights. So I'm defining C as my objective. I want to minimize those paths. And I know in terms of, I have this optimal solution property, structure, that if there is a node here, intermediary node, let's call it T, if this is the shortest path, then this gotta be a shortest path, this gotta be a shortest path. So we already said this many times. So I want to think of a dynamic programming that I'm going to think of T being like the last. T is the last node to get to V. And I'm going to say there's, I'm going to add here a parameter, say K, is the shortest path, with at most K edges. So I'm saying I want to build up this property with dynamic programming. This is the shortest path. So who's going to be C of 1 of UV? The best path you can find with one edge. So that is the edge UV. Because if you only one edge, you can only use the direct edge if there is one. If you need to use 2 or 3 edges, that's not allowed here, right? So how can I write that in terms of this? I could say CK of UV, it's either a path that has C goes to here, CK minus 1 between U and T, right? This is a path of length K minus 1, and this is the last edge. So that will be plus what edge? TU, right? TV. Or maybe this is exactly K edges. Or looking for kth edge. Or I can go maybe with a path without T, right? I'm not sure how to write that down. Is that correct to say k minus 1 from u to v? So this is the best way to go from u to v, only using k minus 1 edges. This is going k minus 1 to some node and then adding an edge. I want to do a little bit of counting here to make sure that this is not. So remember counting, we don't want to count things twice. Although if we run a mean procedure or max, even if I have things enumerated more than once, that's okay. But we want to make sure to count, to look at everything, right? Am I missing a possibility if I say either you use k minus 1 direct edges, or you use k minus 1 to some vertex and then another edge? Is there any possibility that's not included here? Either use between u and v k minus 1 edges, which presumably is a sub-problem I already solved, right? Or you have to find a path to some t, which would at most k minus 1 edges, and then add the last edge from t to v. Is there any path between u and v that's neither one of those things? Is anything counted twice here? Or possibly counted twice? Is it possible that a path this way, it has actually k minus 1 edges overall? So what I'm asking is it possible that a path from C to U with at most k minus 1 edges plus the last edge, actually it's the same as a k minus 1 edges from U to V path? That's possible. How can I avoid this? If I want, again, counting things multiple times, as long as I'm going to say I want the minimum of all these things, right? Minimum. Right? It's okay to have something listed twice, just more effort to go through all these possibilities. If I want to avoid not having this property, like any k minus 1 path in here cannot be in here, how should I do that? Instead of at most, say what? If I change it with exact, can now I have the same possibility in both cases? Can a path that has k minus 1 edges to t and another edge be the same path that has k minus 1 edges exactly between u and v? No. So that's something to think about. Do I want at most of exact here? I don't think that hurts me in terms of computation, like the exactity. It may include multiple paths that I need to consider. But as a recursive definition, again, is this correct? It's either this or that? Every shortest path must be one of k minus 1 edges or less. So the problem with exact is that now I don't have something in here. If I say exact, there is a possibility that's missing here, which is less than k minus 1 edges. What if the true shortest path had 2 edges? That's not in here anymore. So if I put exact, I'll have to list k minus 2, k minus 3, all the way down. So I don't like exact. I like at most, because now I'm including all possibilities, but some of them may be included twice. Some possibilities in here might be already included in there. What about this t? Who's t? Remember dynamic programming? Sometimes we didn't know who t is. So what did we do? Look for it or search, right? So we have to search for t. That is try all the t's, right? Try all the t's and see, do you get that ck minus 1 to work better, or trying all t's that have a edge to v, right? All t that have an edge to v. So I think this would work. How do we actually write this? How do we solve this computation table? For k equal, what order do I need on k's to solve subproblems? For small k's to big k's, right? So in order to solve k equal 100, I need k equal 99 to be already solved. So for k equal 1, 2, what's the maximum k that I need? How many edges can it be on shortest paths? V, right? Something like V. Then, how do I do this? For each UV pair, I'm going to say C at level K of UV. K is like effectively a parameter inside C. I just choose to put it outside for simplicity. Is either this, I start with saying, okay, it's the previous one, right? But then I go for all t's, for all t's that has an edge to V. I check, I say ck of UV is the minimum between, actually let's do the if thing more explicit. If the ck minus 1 of who? U2 P plus the edge EV is better meaning smaller in this case, than the current CKUV, then I make CKUV be CK minus 1 UT plus the edge EV. And then if I want to keep track of something, right, would be SK UV what do I keep track? Last edge. I always keep track of the last edge. Last edge is? Or the last vertex. I could just keep track of T. So, how bad is this? How computationally intensive is this? Did we get it right? Worst case, how many operations? Is this a constant time operation inside this loop here? So then I have, this is n because it's v vertices. This is v squared because it's a pair. And this is another v. So the whole thing might be v to the fourth, right? Because this is a pair. Pair means v squared. V fourth. How does this compare with the naive Bellman-Ford? V square E is better than V fourth? Or same?
Worst case, same.
Worst case same, but generally it's better. I didn't achieve anything, right? That's okay. Failure is the mother of so that's okay. But I want to think of this procedure a little bit in terms of kind of. I have my mind on matrices. That's how I woke up, right? So I wanna think of this as a CK is a matrix, right? Because CK UV is actually a matrix. There's a bunch of V by V values in it. So I want to think of this as a CK minus 1, right? Plus, I want to invent a new operation here, this operator. Right? way. That's not a multiplication, it's Virgil's operator. Times something, maybe the adjacent matrix or something on the graph that says what happens in here. I compute these CK matrices first for k equal 1, then k equal 2, then k equal 3, then k equal 4, right? And how did I compute it? I look at the previous matrix, CK minus 1, and I do an operation with the adjacent matrix, which is not multiplication. It's this thing. Check if that, then that, right? Is it okay to think C2 is just C1 operated with the adjacent matrix of the graph that way, and then C3 is C2 operated with that? C4 is C3 operated with that, so on and so forth? I think that's okay to think about it that way. This operation, this magic operation is this update here. Right? Remember though for multiplication what we said? Adjacent is a constant thing, right? How did we do if we wanted to say CK is CK minus 1 times a fixed matrix A? That means CK is actually A at K, right? It's A times A times A in a matrix operation. But we learned in matrices some trick to do this faster. To say you don't need to multiply A with A with A with A n times. Because we're really going V times here, right? There's a faster way of doing it. Remember that?
Yes.
Repeated squaring, right? And instead of n operations, how many operations did I do with repeated squaring? Log n operations. Can I do the same trick here? To say, okay, can I do repeated squaring? But it's not on multiplication. Has to be repeated squaring on this operator. If I could do that, if instead of this being a loop of V things, will be a loop of log V things. So that will be what? If I could figure out how to do repeated squaring not for multiplication, but for this magic opera. That's your homework for next time. To say, okay, if you do it fast, the details are in the slides, but also in the book, how that works. So let me just check V squared log V to be the correct thing. I think it's V squared log V. Yeah. Exactly for this reason. If I manage to do something like the repeated squaring trick for my new operation, the update, because it has the same shape as matrix multiplication, right? Every CK is CK minus 1 operated against the fixed, the adjacent matrix of the graph with the weights doesn't change. It's the same matrix that applied to the operator here. Just like multiplication would apply the same matrix to multiply with. Can we somehow do some repeated squaring to solve the log V times instead of V iterations? And if we do that being V3 log V, how is this compared to Bellman's 4 now? We said worst case in dense graphs, that's V4. In average graphs, this is like between V and log V. So if it's log V, it's roughly the same, right? So this is something we need to do. And then there is another way of doing it. We'll talk about that on Friday. I still don't have meters. I'm very close to the meters, okay? I don't want to make promises because I have to break them. But yeah, this week I'm pretty sure we'll have meters to look at. Let's throw a big party before I return the meters. Because party is going to be quite hard to achieve after the meters are returned.